So to continue with the oscillations, let's find out the energy. The total energy is always kinetic energy plus potential energy is the total energy. And for how do you find the kinetic energy? The kinetic energy is given by half mv square, in which in this lesson what is, we took x as a cos omega t plus phi naught. Okay, and as you know, this expression itself explains that the rotation starts from here, which is the maximum position or extreme position, and that's why we use this. And it's going to, this will be the initial phase, and this will be the omega t. And the other case is when it is sine, and then obviously there will be no omega, no phi naught if it's going to start from here, but there will be a phi naught if its starting point is going to be here instead of this origin. Okay, so then we had already taken in this whole lesson that x is equal to a cos omega t plus phi naught, and on differentiating this you get velocity minus a omega sine omega t plus phi naught. You know this expression, and instead of sine you can write 1 minus cos square omega t plus phi naught. Cos omega t plus phi naught is x by a from the first equation, so root of 1 minus x square by a square is minus a omega into, okay, so then minus a omega root of a square minus x square by a when it gets out of the root, and a get cancelled. Thus the velocity at any instant is omega. You know this, I've dealt with this in the previous video. With this formula you can find the velocity, maximum velocity, which is at the mean position, to be omega a, and the velocity at the extreme position is 0 considering x is equal to a. So coming back, you can substitute this formula in here. So it's half m v square. When you substitute, you get omega square into a square minus x square. Once again, sorry, therefore continuing this, you can substitute this equation in v square, and you get this to be the kinetic energies formula. Okay, so you know omega itself is root of k by m, so omega square can be replaced as k by m. M and m get cancels. It's also half k a square minus x square, and this is pretty easy formula to remember. This is the kinetic energy. Supposing the question is about extreme position, you can substitute x is equal to a, the kinetic energy will be 0, and at the mean position x will be equal to 0, and so the energy will be half k a square. And to find the potential energy, to derive the potential energy, you know force is proportional to x. F is equal to minus k into x, and so dw is equal to f into dx, which is minus kx dx, which we have already learnt in the lesson work per energy. So integrating both sides, you get half kx square, because integration of x dx is x square by 2. Half kx square is the potential energy. And so the total energy therefore is equation 1 plus equation 2. The total energy is kinetic energy plus potential energy, which is half k a square minus x square plus half k x square. The half k square component will get cancelled. The total energy will remain half k a square, which is the total energy. At any point of time you add potential and kinetic together, it will be this, okay, half k a square. So and that k can again be replaced as omega is equal to root of k by m, so omega square is equal to k by m square, k by m, and k is omega into omega square into m. You can always replace things using that one formula, but this is general formula. Okay, so let's go to the graphs. The graph part of it is, this is a graph between for the position plus a and minus a. And there's one graph which is like this, another graph which is like this. The fact that this is at a maximum position and the velocity is 0, the kinetic energy will also be 0. And this is the potential energy graph, and so you can just draw a line connecting these two, and the total energy will remain to be potential energy plus kinetic energy at any instant. This is the graph you must draw. And the next thing, and you should also be aware of this graph, which they might ask you, the graph between energy and time. So in that case, you know the time period capital T can be broken down into T by 4, T by 2, 3T by 4, and T. This is the total time period. So then you have to draw this graph, and supposing in our case we have been talking about This it's starting from, supposing this is the total energy graph. They're drawing this graph like this, okay. This is one graph, okay. There is also a red color graph which goes like this from maximum, this 0, this maxima here, 0 here, goes up to maxima. So the fact that for one full time period, if you're going to again start from the extreme position, which is the case we have taken, because we have taken x is equal to a, so a cos omega t. So taking it from the extreme position, here the kinetic energy will obviously be 0. And so this is the graph of kinetic energy. Again, this will be the graph of potential energy. Okay, I'm sure you understood this. So let's go to next. There are many numericals based on this, which are all straightforward numericals. You can try from Aurora, and I have already sent you a couple of numericals video. You can use that also. So then oscillations due to spring. Next is oscillation due to spring. This again we have learned it in the work power energy lesson. You have a spring and you have this block. This is an equilibrium position, and supposing you want to stretch it, and it's going to get displaced by a distance of x, and the restoring force will be acting in the opposite direction when the stuff for the spread string, and this is for a compressed spring. The restoring force will be in this direction, and this is the distance from the mean position that's moved. Okay, in this there's no force, but in this the force, restoring force, is happening in these directions. And so you again you know that you're going to get that, the differential equation here is d square x by dt square plus omega square x is equal to 0. You know this equation. And so you also know here again f is proportional to x, f is equal to minus k into x. Energy is equal to half kx square. All that you've learned previously you can always write. And mass into acceleration is equal to minus k into x. M into d square x by dt square is equal to minus k into x. Take it the other side, you get m into d square x by, this will become k by m, and a k by m is omega square, and hence you get this equation which you already know. Just write the differential equation. And to find the time period, omega is equal to so time period itself is directly 2 pi into root of m by k, and that's the formula again. We found the time period, okay, because omega is root of k by m, and so then substituting you get this answer. Time period is equal to 2 pi by omega, and substituting omega here you get this formula. And then they ask you frequency, you can reciprocal this and write it as root of k by m. So that completes for a spring arrangement, the oscillations. What is the time period and frequency? How do you write the simple harmonic motion there? Then is what happens when you're going to suspend the spring like this. You're suspending a spring like this. There's no weight or anything, so this is going to be a relaxed state. It's going to be a relaxed state. Now you're going to put a weight connected to it. The string will get stretched to a bit, and this is where the weight of mass m is, and due to mg which is acting downward, definitely there will be a stretch d, correct, in this direction. And the best part is that the d and mg are in the same direction here, so you can write mg is equal to kd. The force is proportional to d, and f is equal to minus k into d, but not minus here, because the force is not restoring force. The downward force mg is equal to k into d, where k is the spring constant. So there is this equation, mg is equal to kd in the first case. And then go for this, you're going to displace, you're going to displace this block down and let it oscillate to and fro. When you do that, it's going to further get stretched, and the mass is here, and it's further moving through a distance of x, and this is going to be moving above and below, so that this total distance it's going to move is now d plus x, and so here there will be a restoring force, and there will be an mg also, and there will be a restoring force. This restoring force value will be mg minus this which is k into d plus x, the spring constant, the force due to spring constant, Okay, so then that's the net force, which is the restoring force, and F is equal to mg can be replaced as kd from the first equation. A kd minus kx shows that F is equal to is just a minus k into x. It only depends on the additional displacement when you're making it to oscillate. This d doesn't even affect our answer. Okay, so that's what it is. And so then you write this, and you can also write the same now. F is nothing but m into d square x by dt square is equal to minus k into x. A d square x by dt square is equal to minus k by m into x. A d square x by dt square, which is the acceleration, and this itself is omega square, so plus omega square x is equal to 0 will again give you the same differential equation. And you know, a acceleration is here, acceleration is equal to minus omega square into x. That so shows that it's simple harmonic in nature. And the same time period applies here, and time period is equal to 2 pi by omega, and omega is root of k by m. So then time period 2 pi into root of m by k. So it's the same value. The force of gravity has no effect on the force constant, and hence the time period of oscillation of mass. The time period, there's no gravity here, can you see? So that's about it. Okay, so let's go to next. Next is different combinations of springs. Let's take this, for example, you have a spring like this and a spring like this. Okay, both of them are made up of different material, which means the spring constants will be different. Let's take this spring constant as k1, this is k2. This is a mass m. This is similar to this also, but this is vertically hanging, and this is got a mass m, and so this is k1 and k2. So in this, supposing you're going to apply a force and move this, displace it from the mean position, so that you're trying to see how it's going to oscillate. You know that this is going, both of them will move through the same distance L. The distance through which it's moving will remain to be L, correct? So then you can take the force on first one is k1L, and the force due to second one is k2L. Of course, with a negative, if it's going to be, you're talking about a restoring force, you have to write a negative sign. The force, total force is minus KL1 minus KL2, and this is minus K into L. So L is equal to L1. L is the same here. L is the same. So it's minus K1 into L minus K2 into L is equal to minus K into L, where K is not getting cancelled, L is getting cancelled. You get K is equal to K1 plus K2. In resistors, if you remember, if something is parallel, you'll write 1 by R is equal to 1 by R1 plus 1 by R2. In series means you'll write R1 plus R2. Here parallel means it's K1 plus K2. Just remember it, the opposite of it, okay? So it's the same for this also, same derivation for this also, okay? But when it comes to series connection of the spring, the length through which this is getting stretched will be L1, this is getting stretched will be L2, because imagine this is aluminum and this is iron. Even though the force is the same, it's getting stretched to different values, right? So you know, force for this will be minus K L1. The force on this will be minus K into L2, okay, and the K1 and K2 will also be different. Both of these springs will have different spring constants, yeah. And so what you do is find what is L1 from this, minus F by K1. What is L2 from here, minus F by K2. So L is equal to L1 plus L2 means minus F by K1 minus F by K2 is equal to minus F by K, where F is getting cancelled, negative signs throughout get cancelled. 1 by K is equal to 1 by K1 plus 1 by K2. The series connection, the spring constants are written like resistors parallel connection, you know, like that, the series, okay? Just remember this, okay? The fact that this is made up of aluminum, this is made up of iron, the length will be different. The stretching for iron will get less stretched, but aluminum will be more stretched. So you can imagine the length will be different, the spring constants will be different. So since the length are different, you are starting that equation by writing L is equal to L1 plus L2 and substituting, and you get this answer. Once you get this in the case of first derivation and this in the case of second, it's parallel series, you can calculate the time period. You know, time period is equal to 2 pi into root of m by k, where k is the k equivalent in parallel connection, which is m by k1 plus k2. And in the second one, its time period is equal to 2 pi into root of m by k equivalent, where k equivalent in this is k1 k2 by k1 plus k2. So you can substitute that 2 pi into root of m into k1 k2. Here you can write k1 plus k2, and thus you get the time period in the case of a second case where series connection. Okay, and when you have to prove it's simple harmonic. Okay, so you know that f is proportional to here it's in the both the cases it is L, but it's you've got k1L minus k1L minus k2L. And so minus L can be taken out common. K1 plus K2 is your force, and this is like F is equal to minus K equivalent into L. Can you see? This is the distance. F is equal to minus K into X. The restoring force is going to behave like this, and that shows that it's definitely simple harmonic, because F is proportional to minus X is always simple harmonic. The same in this case also. You know that you're going to find the total force, and the total force in the case of series is F is equal to minus k1 k2 by k1 plus k2, which is the parallel thing, into X, and that shows that this is also simple harmonic. Okay, with negative sign, and X shows that simple harmonic. So next thing is about so parallel and series springs. They might ask you questions based on this. Should be able to answer. So then is the pendulum, a simple pendulum, and let's take a simple pendulum. And supposing this is mg, which is acting downward, you know this will be, if this is going to make an angle theta with the vertical, this is theta, and so this will be mg cos theta, and the restoring force will be mg sin theta, which is going to bring it back to the equilibrium position. And this is the tension in the string, which you already know of. So in this, you know, the restoring force is mg sin theta. And what is sin theta from this equation? If you're going to consider this displacement is x, and you can write sin theta to be x by L, where L is the length of the pendulum, which will form the hypotenuse. So then F is equal to mg into x by L. So F is equal to mg by L into x, and insert a negative sign without forgetting, because the restoring force is bring it back to the mean position in negative x direction. And so then therefore you write it like this. And once you write like this, can you see F is equal to minus k into x, where k in the case of pendulum is mg by L. That's the value of k. So you can write what will be the time period. The time period is 2 pi into root of m by k. In the case of k, you can write here mg by L. So m and m get cancelled. 2 pi into root of L by g. If you remember, we must have learned this formula in the first chapter when we were doing dimensional analysis. So that completes this derivation. I made it very simple. Just follow this through. And let's go to next is a simple harmonic motion in a U-tube manometer. In a U-tube manometer, generally the mercury level will be occupying the same level. There's no pressure difference, not measuring any pressure. Supposing let's consider this height as h, there's another height column h here. The total height column of the mercury is 2h, and this is the area, and you want to find the volume that is inside it. It's 2a into h is the volume. Why I want to find the initial mass of this mercury, and to find the initial mass, density is mass by volume. Mass of the mercury column entirely is density into volume, which is density of the mercury into a into 2h, and this is the mass of the original mercury column. Now this is due to pressure variation. You know, this is the varying height, where this is having a height to 2y. From here to here, it's varying at a height to y, and because there is a variation in the height here, this column will exert a force downward, and that weight is going to push it downward. And you know, 2y being the height and area being a, the total volume of the liquid that's going to push it down is a into 2y. That's the volume, but I need the mass of the fluid which is going to push it down. and the mass density is mass, and the mass by volume, mass is density into volume, which is new volume of water. The density of the mercury remains the same, but the volume is A into 2y, and that is a new m dash, which is responsible for the restoring force. But I've got only m dash here. To convert into force is m dash into g. So it's rho A to G Y. Because restoring force, I put a negative sign. F is equal to minus rho A to G into Y shows that F is equal to minus K into Y. And so this is the K. In the case of mercury, the density of the mercury, area, and 2 into gravity, and that's the formula for K. Okay, the spring constant, or here there's no spring, but the factor which is responsible for bringing it to the restoring, and the nature of the liquid it depends on, and the density of the liquid, and also the area. Gravity is anyway constant. It depends on the U-tube manometer's area of cross section and the density. Okay, so you find your K, then immediately they ask you for time period. Time period is root of 2 pi into root of m by k, where in the case of m and k, this is your original m, which is equation 1, which has to be substituted here, and this is your final k, which has to be substituted at the bottom. So substituting that, you get 2 pi into root of what is m, rho A to h, by what is k, rho A to g. Rho A to get cancelled, so 2 pi into root of h by g is the formula for time period that you get in the case of mercury column. But yeah, one thing that I have missed here. Okay, 2y, everything is correct. 2 pi into root of h by g, this is the correct formula. So the time period of oscillation has been found out. If L is the length of the liquid column, so supposing, see, in this I have taken it as 2h, correct? The initial liquid column, 2h. Suppose they change that question and they say that total length is L, which means a 2h has to be replaced as L, correct? And so wherever 2h is there, you can replace it as L, but you have only h. So 2h is equal to L, h will be L by 2. So in that case, you can write it as 2 pi into root of L by 2g. So remember, it all depends. We have taken the initial height to be h here, and h here we have taken it as 2h. Supposing in the derivation they say the total mercury column initially itself is L, then you know 2h is replaced as L, and so you get this answer. So let's go to the next derivation. You have there's this earth, and we are doing a tunnel across the diameter, along the diameter, and we are dropping a small ball, or we are digging this tunnel, and you're dropping a ball, and supposing that ball is at a depth of d from the surface of the earth, and the radius of the earth is r. I know from the center it's r minus d, and that will be equal to y. And gravity at a particular depth is gravity on the surface into 1 minus d by r, g into r minus d by r. The fact that r minus d is y by r, so r minus d is y, g by r into y, and this is the gravity, and the force on it is the restoring force, where you have to multiply mass of the body into gravity, and mg by r into y with a negative sign will give me the restoring force. The fact that F is equal to minus k into y, where y is the distance, shows that my k becomes mg by r in the sum, where r is the radius, m is the mass of the body, and r is the, so mg by r. Once you know the k, you can write t is equal to 2 pi into root of m by k, where in the case of k, you can write mg and r there, and m get cancelled. So 2 pi into root of r by g is the time period in this case. Okay, the next derivation is about the cork. You have a beaker which consists of water, and you have a rubber cork. You have a cork here. Okay, and let's consider that the entire height of the rubber cork, the cork is h, and this distance under which it is there in the water, let's call this distance as y. The part of the body which is immersed in water, that height is y. The area will anyway remain the same for the top and bottom. Okay, so you should calculate upthrust. The first point that you should remember in this is you should calculate upthrust, and upthrust according to the fluids lesson is nothing but the weight of the liquid displaced. Weight of the liquid displaced is a mass of the liquid displaced into gravity, and mass of the liquid displaced is density is mass by volume, mass is density into volume, density of the liquid into volume of the liquid into gravity. However, the volume of the liquid, this is about displaced, is according to Archimedes principle will be volume of the body immersed part into gravity. So what is the volume of the body immersed is A into Y from this diagram, you know. So replace it as A, Y and G, and that is the upthrust, which is the restoring force. In other words, with the minus sign, you can move this Y to the other side. So you get F is equal to minus rho L A G Y, where this is like a K, and F is equal to minus K into Y. That's the condition for restoring force, where K is density of the liquid into, which is here the water. Remember that it's the density of the water into area of the cork into gravity. And so then you're going to put it in time period. You're going to put it in time period. Time period is equal to 2 pi into root of m by k. In the case of k, you just found this, you can plug this in. What about this mass? This mass is completely to do with the mass of the body, and mass of the body is density of the body into volume of the body, which is the total volume of the body, which is A into H. So on substituting, 2 pi is root of m is density of the body into area into height by k is density of the liquid into area into gravity. Area and area get cancelled, thus you get the time period. Okay, so that's this derivation. We still have more. I'll just solve the doubt here and then continue to do with it once again. So that's about the rubber cock. Okay, and is there any other thing that I am missing here? Yes, there's one more derivation, which is the angular oscillation of a balanced wheel of a watch, to prove that it's simple harmonic. Okay, balanced wheel of a watch. So you know the balanced, that there will be a torque which is proportional to theta, and torque is equal to c into theta, because there will be a central axis about this is a central axis, and there will be this what to say, the configurations, and the needle will be moving around like this. See, let me explain to you in detail. This will not come, they don't ask this, but still I'll explain to you. There is a wheel, okay, to which the pointers are attached to. So the wheel will rotate. This wheel will rotate slowly, and as the wheel is rotating, there is also a hairspring which is like this. Hairspring is like this. It's a thin wire. Okay, as the wheel rotates, this will also get twisted. Okay, the wire will also get twisted as it keeps rotating, and so then this is undergoing this hairspring, as they call it hairspring, and this is undergoing a torque. When any rotation is there, obviously torque is equal to proportional to theta, and torque is equal to c into theta, and that c theta which is the torque, which is also equal to I into alpha. You know, torque is equal to I alpha. We learned it in rotational motion lesson. So equate both of this. That's the condition. Make sure you're putting a negative sign because it's a restoring torque here. Okay, so then c theta is equal to minus I into alpha is nothing but d square theta by dt square, which is the acceleration. So you get a new differential equation for this. You can bring the I down and cancel this, and take them to the one side, d square theta by dt square. So this comes this side, plus a c by I into theta is equal to 0, and that will be a differential equation. Or you can just leave it like this. Okay, just leave it like d square theta by dt square is equal to minus c by I into theta, and this is like an acceleration is equal to minus, this is like an omega square here into theta. What is, in this case, what is omega is root of c by I, where c is a constant of proportionality that is coming in this torque, which is called, they call it couple per unit twist. Okay, it's a constant. Say for example, if a wire is getting twisted, if it's aluminum, it will get easily twisted. If it's iron, it will get the twisting will be it's very hard to twist it, so like that constant is what is called coupled per unit twist. This derivation, this is a very very unimportant equation. They never ask this, but in case they ask you what is omega in the case of a balanced wheel of a watch, then you should be able to write this. And so you know that omega is basically root of c by I, and so time period is equal to 2 pi. So time period is 2 pi by omega, and so 2 pi into root of, substitute omega, 2 pi by omega, so 2 pi by omega, the c comes here and I goes there, and 2 pi into root of I by c. So this is a derivation for time period in the case of the period of oscillation. In the case of a balanced wheel of a watch, if they ask you this, you write, but mostly this is never coming. Then I'll also explain to you about a free oscillation. There are three types of oscillation. One is free oscillation, then damped oscillation, then maintained oscillation. Okay, so let's talk about free oscillations. If a body capable of oscillation is slightly displaced from its main position, slight nagatram, and left to itself, it starts oscillating with a frequency of its own. Correct? Such an oscillation is called free oscillation. So a body which is displaced from its equilibrium position, when left, disturbed from the equilibrium position and left, then obviously it starts oscillating with a frequency of its own, such is called free oscillations. It oscillates at the natural frequency of the body. It freely oscillates, and this is called natural frequency of the body, and that frequency is reciprocal of time period again, and time period is 2 pi into root of m by k, and so then the frequency will be 1 by 2 pi into root of k by m. And so the important features of the free oscillations are, in the absence of dissipative force, that is, if there is air resistance, it will not continue to oscillate, right? It will come to, if there's all air resistance, it will come to rest. So they're saying, or it has to overcome the air resistance, so there will be dissipative forces. Okay, such a body, if in the absence of dissipative force, then the body will vibrate with constant amplitude and fixed frequency. It will continue to oscillate in the same way throughout if there is no resistance offered beautifully, and that is called undamped oscillation. Undamped oscillation. Okay, so then basically in undamped oscillation, the frequency is going to be the same, the amplitude is going to be the same, it should be equal. Okay, just draw this, and this is x of x and t, x of t, and this is the diagram. This is for undamped oscillation. What is damped oscillation? That will be like it will get damped. What to say? It will get decreased. So that's what it is. Can you see it's getting damped? And obviously then there's the air resistance. It is trying to, all its energy is getting wasted or overcoming the resistance offered. Such is called damped oscillations. Damped oscillations in which the amplitude continuously decreases gradually with the passage of time. And these are called damped oscillations. Okay, so it changes the simple harmonic motion into periodic motion. You cannot call this a simple harmonic, whereas this is simple harmonic. Whereas this cannot be called a simple harmonic, it can only be called periodic. Yeah, that's all. Okay, that's very important. It slightly reduces the frequency of oscillation. This is a constant frequency and constant amplitude, whereas this is slightly reduced frequency. Number of oscillations also slowly dies down per unit second. Okay, so that's about this. So what is maintained oscillations? To an oscillating system, energy is continuously supplied. You supply external energy and artificially make it oscillate without, even if there is air resistance, with the external force, make sure that it's getting sustained. That's called maintained oscillations. Such oscillations are maintained oscillations. The system oscillates with its own natural frequency again, but that will behave like this. But only thing is, you are giving an external supply of energy to it. That's the only thing. Okay, so that's about this. And any other topic remaining? Yes, there is There's one more topic remaining which I have to talk about. I don't know if this is there in portions though. Okay. If it's there, you let me know and I'll release a video. I think this is what it is, and I'm done with the lesson. In case you have any other portions that I need to do in this lesson, please let me know. I'll make a video and send it across.